So, hello, welcome to the talk Rust Embedded Async All the Way. We know it's the talk right before the beer, so we will try not to be too much in time. But yeah, let's get started. So who we are? So this is
Ulf. Yep.
This is Ulf, and this is me, Jens. So we both work as software engineers at Red Hat. And what do? We work on open source IoT, cloud embedded stuff. We focus on the project Rogue IoT, which you can see here. We have a nice logo. So that is what we do. And it's double clicking. Yeah. So the question is, why Rust? So this is one question. So the question to the room, please raise your hand if you have tried out Rust. Oh, that is awesome. Please raise your hand if you're using Rust in production. Okay. So what is Rust? They define themselves as a language empowering everyone to build reliable and efficient software. If you create a new language, you wouldn't settle for less, right? So that's what you write on your homepage. But no, it's double clicking. So if you take a look at a report from Microsoft, they found out that 70% of the vulnerabilities that they find, that they assign CVEs to, are memory safety issues. So you have C program, just access memory somewhere and mess up the memory. And they try to bring that down, but we're not able to. Now, the thing is, what does it mean? It means 70% of those issues would not have existed had they used Rust, because Rust prevents you from those errors during compile time. So there's a tweet that just got tweeted recently, and that is the CTO of Azure, Microsoft. And you can read it for yourself. What it basically, maybe take a look at the last sentence. The industry should declare all those languages deprecated, meaning C and C++. Stop using that language. That's a very bold statement, but you see it comes out a few years after this report that we had. So maybe recall EclipseCon 29. There was a talk, A Tale of Rust, the ESP and IoT. So that was a talk to get you excited about Rust on microcontrollers. So microcontroller like this one, and Ulf will go into a little bit more details. There was a little bit of, I don't say cheating going on, but it was a little bit optimistic regarding Rust. So there was an application up front, and this is the slide from the talk back then. There was the application sending data to the EclipseCon system in JSON format. So there was JSON in Rust. There was all kinds of other stuff in Rust. But a big chunk was actually the ESP IDF consisting of 3 RTOS, which is not Rust. And I think we can do better, and well, we did, and this is where I hand off to Ulf.
This is a JavaScript. This is a JavaScript bug, not a Rust bug. Just to be sure. So yeah, we've been doing embedded Rust for a while now, and there's a lot of questions. What does embedded mean? You talk to some people, it means Linux. We're going a bit smaller devices than that. Usually you have very little RAM, also limited storage. You don't have operating system facilities to help you out, no memory allocator. So it's a very, in some ways, restricted environment, but also quite free in the sense that you know exactly what your application is doing. So there is a working group as part of the Rust language ecosystem called the Rust Embedded Working Group. Screensaver. Okay, so it's just a community, informal community, to collaborate on Rust embedded topics. There are people interested in specific protocols. There are people interested in specific hardware, porting Rust to run on that hardware, and and they have weekly meetings to sort of discuss any issues, and they maintain a few core libraries that are widely used among a lot of these driver specific or chip specific libraries. You have the Rust compiler. It supports several architectures pretty well now. The Cortex-M architectures from ARM are by far the most well supported, but you also have architectures like RISC-V, and also the other architectures from Espressif, the Extensa, is also getting support and seems to be close to being merged in LLVM. An application for the microcontroller is structured in its different layers. At the bottom you have the hardware, and above that you have what we call a peripheral access crate. This, but when I say crate, it basically means a library for those who haven't, played Rust yet. And the pack basically contains type-safe register access, so you basically can be sure that you don't set the wrong bit if you use the type, right? And already at that level you get some protection and safety using Rust. But as most of you probably know, that doing a SPI transaction involves more than just writing to a single register. There's coordination across different registers and peripherals that needs to be enabled. You need to disable them, and power saving and so on. So at the layer above that you have things like the hardware abstraction layer, or HAL as we call it, which provide a more generic driver for SPI or I2C, or also very common peripherals that you find on hardware. And there you have like a interface to just write a byte array to over SPI, and that will use the peripheral access crate to set up the registers and so on. So at that level you can actually use safe Rust, as we call it, where the HAL kind of guarantees that the registers are accessed in a safe manner, and that no two parts of your application can actually use the peripheral at the same time. Things like that. So if you're writing software or a driver that needs to use an SPI device, then having like API or trait to be able to use in that driver is very useful. So you might have a generic driver for a sensor that communicates using SPI. You want to make sure that it works with different types of hardware. So these hardware abstraction layers, they implement a common set of traits which are maintained by the Rust embedded working group. And then people meet and discuss to agree on the APIs, which isn't all trivial, but it's a very collaborative effort. And on top of that, again, all of these things are kind of optional depending on what your needs are in your application. So you just want to use the register directly, like you would in an application you want full control of everything, and you have maybe some special requirements. Then yeah, you can do that. So for creating Rust applications, you can use like these. Just write plain Rust, and you need to. If you do that, then you need to sort of configure your interrupt handlers and make sure if you don't have any concept of tasks and so on. And what's very common in these real-time applications is that you need some kind of task scheduler or a way to group different pieces of your application. And you have a framework called Arctic, which is very popular. And you also have an project called Embassy, which is what we are using in our application or example applications, which is focusing on more on async Rust. And that's kind of what we want to spend a little bit more time talking. I just need some water. Oops. Oh, it's jumping again. Oh, it is. Okay. Oh, okay. That's just correct. So if you're not using async and ignoring this direct register access, you would use a hardware access layer, and you might have defined some types for a button or a LED, and you would sort of busy loop waiting for the button to be pressed down and then blink your LED, right? And the problem with this, it's inefficient. So you'd use interrupts in order to make this driven by hardware. And the problem with that in Rust is that you're not allowed to take those shortcuts that you might be used to in C, like I know this is safe. But in Rust, if you either go down the dangerous path of using unsafe, or you have to use the types that actually enforce safe access to shared state. So you use a mutex, and then you can't initialize the mutex directly globally, so you need to use an option, and like your application gets a bit ugly, as I like to say. So that's where async really shines, in my opinion, because rather than having to deal with setting up the interrupt and waiting for the interrupt to be invoked and then resuming your application, you can let the HAL and an async executor do that for you. So if you can remember the blocking application, the only difference here is that we have a wait change line, which awaits the button to change its state, and that's internally setting up the interrupt handling and waiting for the interrupts to fire, and then it puts the microcontroller to sleep while it's waiting for that. So this is very power efficient, but it's very easy to read compared to a lot of this interrupt logic. To use this feature in Rust async, you need an executor. This is similar to what you call Git generators in computer science terms, where you have a task scheduler or something that's able to decide which task to run, or a coroutine. And for this, when you're using the standard library in Rust, if you have, then you probably heard of Tokyo, which is an executor for that, which is great, and we use it a lot in our server-side components. But on embedded, Embassy is kind of the similar story, but of course with a few more restrictions because there's no memory allocator. And that's ultimately one of the differences between the bare metal and standard library is not only the memory allocator, but some of the collection types that you have in Rust are not available. But they are available if you know the max size of your collection, things like that. And ultimately they have different, let's say, target applications in their use, where you use the no-STD usually for like bootloaders, bare metal firmware, or an operating system kernel, for instance. A little bit more on Embassy, the executor for async. It's supporting a lot of these common things you need to do, like wait for 10 seconds, and it sets up the internal timer peripherals of the device to do that. so that you don't need to sort of configure the timer, pass the timer type around, all of that stuff. That's just available. That's again, that's something you probably is sufficient for a lot of applications. For those who don't want to do it like that, you can still, create your own timer and use that. So the whole thing is kind of built to be extendable and also configurable with existing Rust public libraries, so that you can sort of mix and match what you want. Other things that is in Embassy is like a bootloader, which we'll demonstrate later, USB integration, TCP/IP, LoRa, and Bluetooth. So with Embassy, you can sort of use that with other crates. We have Ector, which is like an actor framework for embedded, because we thought, hey, it would be cool if we could have that for embedded devices as well. And it works really nicely with Async. And the stuff we're doing at Red Hat is usually put into Drogue device when it comes to the firmware side, where we use Embassy, build on Embassy, and implement support for some boards we use, supporting over-the-air updates, integration with Drogue Cloud, and so on. And the last thing I want to say, because usually, like with C or C-based applications, you have FreeRTOS, Zephyr, yeah, probably more frameworks I've forgotten, and they all require you to buy into their build system, their way of doing things. You have everything stored in a single repo that project manages. But that's totally different in bare metal Rust. Basically, the Rust ecosystem and language is reused for embedded, and it's just like you can write an embedded application and a regular application, and you use the same tooling. There's tools to flash most microcontrollers, run the debug probes, and so on. And that's just blow my mind when I was started with Rust. And you can sort of pick and choose the stuff you need. You can pick a real-time scheduler and use that together with some other library, right? Where you don't have to use this because this is what the project uses, kind of. So it's very free. Oh, sorry. So it's time for a demo.
Yes.
And I need to resize the window a bit, maybe. How do I do that?
There you
okay,
go.
there you go. So what's going to happen here is that Jens is playing a game.
You might have seen it at the Red Hat booth.
Yeah. And although, I'm nervous, so it's warm in here, but it's not 80 degrees Celsius at least, I think. So we need to fix this bug that's on his microcontroller controller firmware. And to do that, we set up Hawkbit, as well as some process running on the laptop here, which talks with the microbit and runs the update. So I'll just start it because it takes a couple of minutes. Just check which version we're going to update. We're going to have the bug fix version. So, okay, so what happens here? So while Jens is playing, Hawkbit will receive continuously status updates from the device, where the device tells it which version it has, what transaction sizes are, like what you call MTU, like the package sizes it wants to receive updates for, and so on. And then Hawkbit will check that against its database and tell it, you need to update. And to do that, the device also runs a bootloader. It's what we call a two-partition bootloader, where you have an active partition and you have a DFU partition, which the new firmware is written to. And the bootloader has some state, which is flipped whenever you want to switch to the other one. With this bootloader is written in Embassy as well, and we have application which actually provides a GET service over BLE that the laptop is running this update process against. To do that, we're using, let me just do this, just see it a bit bigger. It's a bit small, but so we have Eclipse Hawkbit. We also have a proxy, if you will, in between, which translates between device and Hawkbit, because the devices don't really like to talk JSON and HTTP, right? That's a bit too heavy for them. So the gateway or proxy essentially translates CBOR encoded messages to Hawkbit, the Hawkbit API, and it's very similar. So we found this really useful when we're going to support multiple protocols other than HTTP, right? So then we just do that. And let's look at the update progress. So we have just a demo dashboard for showing the current updating state, where you can see the current versions with the bug and then the target version being updated too. And while we're waiting for the final bits to be received, let's look at the comparison of in a blog post that some guy in the community wrote about Rust versus C. I'm not sure if you can see this, but I can give you the link afterwards if you just come and talk to us. So now you can see Jens has stopped playing. That's because the bootloader is swapping the firmwares. And it won't reappear until it's a swapped image. And it should connect again, yes. Now we have the bug fix version, as you can see. And it should show the correct temperature if that thing is... It's showing the acceleration data, and yeah, there the temperature is. So now it's in Celsius. It's still a bit hot, but I blame the uncalibrated temperature sensor for that. Yeah, I guess that's the demo part.
Wrong window. So yeah, maybe just to recap. I need to stand there, right? So just to recap, so we just saw a device update, a firmware update of this device over the air while playing the game. And this all including the Rust firmware from the bootloader to the application app. So this is like the improvement over the talk a few years back. And if you take a look at what in this time the Rust community, the Rust embedded community has achieved, I think this is really awesome. And also in the same time, the other Rust community with the backend application and also front-end WebAssembly has made huge improvements. So again, I can only say check it out. If you already take a look at Rust, that is awesome. Keep going. There will be much more stuff to come. So if you peek around and see even the Linux kernel, we will have Rust, or there is already Rust now in the newest version. So I think this is something definitely to check out and use in the future.
And a big shout out to Dario, who who started the Embassy project, which we're collaborating with upstream, and he's done a fantastic job there.
Okay, thank you for listening, and if you have any questions. Hand you over the mic.
Thank you. Good afternoon. Thank you for the presentation. It was very interesting. Are you using Embassy and Rust Embedded in production at the moment? And if so, would you recommend it, or would you say we should wait for?
Well, at Red Hat, this is the closest to production we are with Embassy. But
fair enough.
But I know there are at least 3 companies using it in production. The one who started the project is using it for the door locks. Is Achilles, I think, is the company name. There's a guy using it for farming sensors in Australia. and another one for what was that? It was like an audio application kind of some kind. So there are different people coming from different companies, different industries. They come, they see, okay, maybe it's not fully supported my use case, but they come and collaborate, and it's really motivating and fun to be in that community.
Thank you.
Any more questions? Oh, please pass on.
Thank you. Yes, thank you for your presentation. So, in your experience with Rust and Async, we saw that using future bring a lot of context within the memory, and it increase a lot the size of the stack usage when you chain all the future together. What is your feedback in the scope of embedded with this?
So you don't necessarily use more stack with the futures, but because what the future is essentially a segmented stack. So rather than having a fixed stack size for your tasks, which whenever you which will be constant throughout the lifetime of the task, that's kind of wasteful. But the nice thing with futures is that they are compiled to be the exact amount of stack you need for what you're doing in the future, right? And then what I find difficult about it, though, is that it's maybe harder to reason about how much memory you're actually using in your future. Because if you have some data and you're passing it through what we call an await point, it means it will be in multiple places. So you have to be, you're right, you have to be careful about the stack usage, but it doesn't use more stack per se unless you're kind of know what you're doing. But it takes some time to get used to, I think. And there are some tools coming to be able to analyze that. So what we have been playing with is that you can actually verify at compile time the size of the static memory you use, as well as the stack usage of all your embassy tasks, which are futures, using a tool called cargo call stack. And that way you can sort of get both the stack usage and the static and get a very good idea on how much total memory your application uses.
Okay, thank you.
I think over there we had a question.
Are some debuggers already supporting to debug on target?
You can use GDB, yeah.
Okay, directly.
Yeah, so I didn't mention that, but there's a library in Rust called probe.rs, which there are some tools that you can use on the command line to interact with both using the RTT capability of the Cortex-M, but you can also it can also run a GDB server, and you can sort of set breakpoints and debug your application on target with that.
Cool.
But you can still use OpenOCD or whatever you want to use. Like you produce a, as long as you have the symbols and the firmware, right?
Was there a question over there? No. Okay, thank you for listening. There's a lot of stuff we didn't talk about because you want to go for a beer now, I guess. We are at the Red Hat booth, so if you have questions, just come by and we will have a chat. Thank you.